Good day. This is your professor, Dr. Miller. I'm going to use an iPad, make a recording for you to view at your leisure. What I want to talk about today on the iPad is the Cantor Set. I mentioned it last time when we met and did a little introduction to topology, but let me just take a minute to say a couple of things about the Cantor Set. Before I get there, let me just make a couple more remarks on topology. Topology is the theory of open sets in a space. And for our case this semester, our space is going to be the real line, and our open sets, they'll all be built from these, what we call the open intervals. And we talked about this last time. We proved that using the definition the book has for open, that these open intervals are actually open according to the definition of our textbook. So in our study of topology, we'll talk about some ideas that you've seen before, but we'll probably recast them in a new light, just kind of like we did with that quote-unquote open interval from A to B. For us now, open means something new. So some terms that are going to be important to us are open set, closed set. We'll also talk about the closure of a set, so we can take a set and make it into a closed set. We're going to talk about things that are called compact sets. Those are going to be really important to us. And compact sets have an idea associated to them called an open cover, so be prepared for that. We'll create things called open covers of a set. We'll also talk briefly about things called perfect sets. If we have time, we'll talk about connected sets. We'll talk about things that are called F sigma sets, things that are called G delta sets. And we'll talk about dense sets. Like we've already seen, Q is a subset of the reals, and it is dense there. But we'll also talk about sets that are nowhere dense. Okay, sometimes these are called sparse sets. Okay, all these ideas here are topological ideas, and we're going to give them all formal meanings, and we're going to use some of these quite a bit. These topological ideas will give us a solid foundation for talking about concepts that are central to the calculus, like continuity of functions, differentiability of functions, integrability of functions, and even something we've already talked about, convergence of sequences and series of functions. We've already talked about that stuff, but we're going to recast these ideas pretty soon in the language of topology. So this is why topology is important for us. It gives us a language to talk about all these important concepts. So the text starts chapter 3 with this crazy example of this thing called the Cantor Set. Okay? And it's good for you to spend a little time thinking about, why is the author bringing this up? This thing seems so weird. Why even talk about it? And we'll talk about that when we meet in class sometime. Let's go through the definition of the Cantor set. So the first thing you need to know is that if this is the real line, and this is the interval from 0 to 1, the Cantor set lives in this closed interval. So you start here. And in fact, we're going to call the set C sub 0, the closed interval from 0 to 1. And we're going to build the Cantor set through an iterative process. Okay, so I'm going to build the next approximation of the Cantor set, call it C1, by taking C0 minus its middle third. Okay, so just to be clear about that, that's going to be equal to 0 to 1/3 union 2/3 to 1. So what I've done in my interval from 0 to 1, I cut it into thirds, and I'm taking out this open interval from 1/3 to 2/3. Okay, and I'm leaving these two closed intervals behind. So C1 is the union of these two closed intervals of length 1/3. And then what I'm going to do is I'm going to say C2 is C1 minus the middle third of the two intervals that constitute C1. Okay, so let's take this, copy it, bring it over here, paste it. So let's continue writing. So C1 minus the middle third. So that means that we're going to take each of the remaining intervals, cut them in thirds, and then remove the middle third of each of those intervals. So what we're left with is the interval from 0 to 1/9 union the interval from 2/9 to 3/9, which is a 1/3, and then the union of 2/3 to, what would that be, 7/9, union 8/9 to 1. Okay, so that's the second approximation to the Cantor set, and then we continue in this way. Okay, so we're going to build the nth approximation from the previous approximation by removing the middle third of all the intervals that are in the previous approximation. Okay, so what do you get? You get Cn consists of the union of 2 to the n disjoint closed intervals of length 1/3 to the n. Okay, so that's what the nth approximation to the Cantor set is. And so we're going to define the Cantor set C to be equal to the intersection of these approximations as n goes from 0 to infinity. Okay, so it's the infinite intersection of these sets. So I guess, yeah. Let me play this game again. So we have the Cantor set. So let's list some properties of the Cantor set. Well, each Cn is a closed set. Okay. And the arbitrary intersection of closed sets is a closed set. So C is a closed set. Okay, so that's kind of cool. Cantor set's a closed set. Maybe I should have started with the second property. It's definitely non-empty, so it's not a trivially closed. It's actually got points in it, because the number 0, that's in the Cantor set, and the number 1 is in the Cantor set, right? And in fact, all subintervals not subintervals, all endpoints of the subintervals of all Cn are in C. Right? The process of creating the Cantor set never throws out an endpoint. It just creates more endpoints. Okay. So that's cool. Related to that, all these endpoints are of the form m over 3 to the n. Okay? And so if you consider all those endpoints, the set of these as m, I guess those are natural numbers, and n are natural numbers, this is countable. So the Cantor set is at least countable. So that's a good question. Is C countable? Okay. We'll see that it's not countable. We'll see that it's uncountable. So, but before I get to that, we can ask how many points are in C. Okay. We know it's at least countable, but consider this. The length of the first approximation, or the 0th approximation of the Cantor set, that's an interval of length 1. And if you look at the total length of the first approximation, I believe you'll get that's 2/3. And if you get the length of the second approximation, that's 2/3 minus 2 intervals of length 1/9, and that's 4/9. And if you keep going, you can see that the length of the nth approximation is the length of the previous approximation minus 2 to the n minus 1 over 3 to the n. Okay. So if you take the limit, we'll see that the total length of the Cantor set is 0. Okay. So if you look at the lengths of all of these Cn's, and you take the limit as n goes to infinity, you're going to end up with a number 0. So that's pretty amazing. It's almost like when you try to look and see how much is in the set, you're saying this is saying there's nothing in the set. So but now we're going to do this. We're going to show that C is uncountable. Okay, so not only are there lots of things in the set, there's many points in the set as there are real numbers, which is kind of wacky. Okay, so I want you to consider the sequence an where an is 1 or 0. So it's the sequences of 1s or 0s. So it's a fact that the set of sequences of 1s and 0s is uncountable. And if you want to prove it, just use a Cantor diagonalization argument. Okay, so what we're going to show is that there's as many points in the Cantor set as there are sequences of 1s and 0s. Okay, we're going to create a correspondence now. Okay, so let's let C be a number in the Cantor set. Okay, and we're going to associate it to a 0 or a 1. Okay, so I'm going to build a sequence AN. Okay, where each of these terms in the sequence are going to be defined as follows. Okay, and this C is going to be associated to this AN in the following way. So remember, the Cantor set is in the interval from 0 to 1. And the first approximation we get by taking out the middle third. Okay, so A1 is 0 if C is in the left part of C1, and it's 1 if C is in the right. Okay, so that's to say, if C is over here, A1 is going to be 0. If C1 is over here, it's going to be 1. All right? So once you've determined that, then you can go to A2. And you're going to say A2 is 0 if C is in the left subinterval of C2, and it's 1 if C is in the right subinterval of C2. So what do I mean by that? Remember, if C, look at the first step, C1. Our point C is in either the left or the right. So suppose it's in the left. That means that it's over here somewhere. And so if it's in the left part, then it's either going to be in the next step in the left piece of that or the right piece of that. And that's how we assign A2. If, on the other hand, C had been in the right part, then even over in the right part's going to have a left subinterval and a right subinterval. And that's how we assign A2. So we keep going, and we assign AN in the analogous way. And so this is how we associate to C a unique sequence of zeros and ones. Okay. Is it unique? Well, that's a good question. We won't talk about it much. Okay. All right. So we will claim, without proof for the purposes of time, that this establishes a bijection between C and the set of binary sequences since the set of binary sequences is uncountable, then so is the Cantor set. All right, so that's the proof of the infinity, or the uncountable infinity of points in the Cantor set. There are some details that still need to be worked out in that proof, but for the purposes of an introduction to the Cantor set, that's good enough. And the reason that we're bringing up the Cantor set is because it's a bizarre set. It has all kinds of neat properties, like that we listed. The set is closed. It's It's non-empty, obviously. It's at least countable. But it has zero length. It doesn't have any meat to it. There's no intervals in it at all. It's all almost like it's isolated points. Okay? But there are more points in the Cantor set than there are points in the rational numbers. So it's a set that has bizarre properties that will come back, and it kind of tests our intuition about what sets should look like. And that's one of the things that happens in analysis. We can come up with bizarre examples that test assumptions that we're making about the ideas that are under study. It was a long time before mathematicians in history understood that there were functions that weren't continuous, or they understood that there were functions that weren't differentiable. It just wasn't part of their paradigm, and they had to work hard to find things that broke them out of that limited paradigm. And that's what the Cantor set will do for us in some situations. So study the Cantor set, get a feeling for how it's defined and some of its properties. Make sure you understand the proofs of the claim and fill in some of the details here that I left out in the proof of the uncountability of the Cantor set. And I will see you next time.